Tonight, we're diving into one of the deepest features of reality itself, gravity. It's always there, holding you to the ground, locking Earth's atmosphere in place, keeping our planet circling the sun, guiding entire galaxies across distances so vast they are measured in billions of light years. But here's the idea that changes everything. Gravity may not be a force at all. It's something far more unexpected and far more elegant. Before we go further, if explorations like this spark your curiosity, a quick like or subscribe genuinely helps the channel grow. It takes a second for you, but it helps this journey continue. Now, let's begin. Think about what you believe gravity is. You let go of an object, and it falls. Straight down. End of story. You've been taught since childhood that Earth pulls things toward it, that gravity is an invisible force tugging you downward, that the sun's gravity pulls Earth into orbit. That explanation works, but it's not the full picture. It's a bit like saying the Earth is flat because it looks flat where you're standing. Useful for daily life, but it hides a much deeper truth. In 1687, everything changed. Isaac Newton published Philosophiae Naturalis Principia Mathematica, often just called a Principia. It became one of the most influential scientific works ever written. Before Newton, explanations for falling objects or planetary motion were largely philosophical speculation. Newton replaced guesswork with mathematics. He showed that the same rule governing an apple dropping from a tree also controls the motion of the moon around Earth and Earth around the sun. This was revolutionary. At the time, people believed the heavens followed different laws in the world beneath their feet. Newton proved they were one and the same. His law of universal gravitation states that every object in the universe attracts every other object. The strength of that attraction depends on how massive the objects are and how far apart they are. Here's what that really means. You and Earth attract each other strongly because Earth is unimaginably massive. You and a pencil across the room also attract each other, but so weakly that the effect is completely unnoticeable. How weak is weak? If scientists tried to build an instrument sensitive enough to detect the gravitational pull of a single person walking by, the detector would need arms stretching roughly from the Sun to Saturn, about 10 billion kilometers. Anything smaller would be drowned out by thermal vibrations and quantum noise. That's why you can feel a tiny magnet snap into place or a static shock from a doorknob, but never feel the gravitational pull of another human standing next to you. On human scales, gravity is astonishingly feeble. In fact, gravity is about 10 cubed times weaker than the electromagnetic force. Why that's true remains one of the greatest unsolved questions in physics. And then there's distance. Double the distance between two objects, and gravity doesn't simply weaken, it drops to 1/4. Triple the distance, and it falls to 1/9. This inverse square behavior is why gravity only becomes dominant when enormous amounts of mass are involved. Planets, stars, galaxies. Newton's equations worked remarkably well. They predicted planetary orbits with stunning accuracy. They explained ocean tides, the slow rise and fall of the seas caused by the moon's gravitational influence. For centuries, this framework described the universe beautifully. But as powerful as Newton's gravity was, it wasn't the final answer, and that's where things get truly strange. These equations also explain something astronomers had long observed. Planets farther from our star move more slowly along their paths. Even more impressively, Newton's framework was powerful enough to reveal worlds no one had ever seen. That's exactly how Neptune was found. In the mid-1800s, astronomers realized that Uranus wasn't following the orbit Newton's laws predicted. The deviations were tiny, but consistent. Instead of dismissing the mismatch, scientists asked a bold question. What if another unseen planet was disturbing Uranus's motion? They used mathematics to calculate where such a planet would have to be. Telescopes were aimed at that precise region of the sky. And there it was, Neptune, almost exactly where the equation said it should be. For more than 2 centuries, moments like this cemented Newton's laws as the ultimate description of gravity. But cracks began to appear. The most famous problem involved Mercury. Its orbit isn't a perfect ellipse. It slowly rotates over time, a motion known as orbital precession. Newton's equations predicted how much this rotation should be, accounting for the gravitational influence of all the other planets. Yet the numbers didn't quite line up. Mercury was drifting ahead by about 43 arcseconds per century, roughly 1/80th of a degree. Minuscule, but undeniably real. Astronomers search for explanations. Maybe an undiscovered planet, nicknamed Vulcan, was tugging on Mercury. No such planet existed. Maybe Newton's equations needed small corrections. None of them worked. The discrepancy remained unexplained. Until 1915. That year, Albert Einstein introduced his general theory of relativity and completely redefined gravity. His idea was astonishing. Gravity isn't a force acting at a distance at all. It's the geometry of the universe itself. At first, that sounds like nonsense. Curved space-time doesn't exactly feel intuitive. So let's build the idea from the ground up. Start with how we usually think about reality. Space and time seem separate. Space has 3 dimensions. You can move forward and backward, left and right, up and down. Time feels different. It flows in one direction, from past to future. You experience moments in sequence. You can't rewind or skip ahead at will. Space feels like where things happen. Time feels like when they happen. Einstein showed that the separation is an illusion. Space and time are fused together into a single 4-dimensional structure called space-time. This isn't just a mathematical trick. It's how reality actually works. You can't have space without time, or time without space. Every event in the universe is both a position and a moment, inseparably linked. When you move through space, you're also moving through time. Even when you appear motionless, you're still traveling through space-time. Everything that happens does so at a specific point in this 4-dimensional fabric. And here's the key idea. Space-time isn't rigid. It can bend, it can warp, and what causes that bending? Mass and energy. Anything with mass or energy distorts the space-time around it. The more massive the object, the stronger the distortion. Earth curves space-time. Our star bends it far more. Even you slightly warp space-time simply by existing. Everything leaves a geometric imprint on the universe. A useful analogy is a stretched rubber sheet. Place a heavy bowling ball in the center, and the sheet dips downward. Add a marble nearby, and it won't roll in a straight line. Instead, it curves toward the bowling ball, guided by the slope of the surface. From the marble's point of view, it isn't being pulled by a force. It's simply following the shape of the surface it's moving across. It's simply following the most direct path it can take. But because the surface is curved, that straight path bends inward toward the bowling ball. The same idea applies to Earth. When you release a ball, it isn't being yanked downward by an invisible force. It's moving along the straightest possible route through a space-time that Earth has curved. From our perspective, that path points toward Earth's center, so we call it falling. Of course, the rubber sheet analogy has limits. The sheet is a 2-dimensional surface sagging into a 3rd dimension, while space-time has 4 dimensions and isn't bending into anything else. Its curvature is internal, built into space-time itself. There's also a logical flaw. The bowling ball sinks because of gravity, which means we're using gravity to explain gravity. So think of the analogy as a visualization tool, not a literal picture. But what does curved space-time actually mean? It means geometry itself changes. In flat space, the shortest path between 2 points is a straight line. In curved space, straight lines don't exist in the usual sense. Instead, there are geodesics, paths that represent the shortest distance within that curved geometry. You already experienced this on Earth. Our planet's surface is curved. The shortest route between 2 cities isn't a straight line through the air. It's a curve along the surface, known as a Great Circle Path. That's why flights from New York to Tokyo arc over Alaska. On a flat map, the route looks strange. On a globe, it's the most direct path. Space-time works the same way. Objects move along geodesics in curved space-time. A planet circling a star isn't being pulled by a force. It's traveling along a geodesic shaped by the star's immense mass. From the planet's own point of view, it's moving straight ahead. From ours, that straight motion appears as an orbit. The planet is always falling toward the star, but it's also moving sideways fast enough to keep missing it. Orbit is simply perpetual freefall. This also explains why astronauts aboard the International Space Station feel weightless. They aren't beyond Earth's gravity. At roughly 400 kilometers above the surface, Earth's gravitational field is still about 90% as strong as it is on the ground. They feel weightless because they're in freefall. Earth curves space-time. The station follows that curvature, and the astronauts fall at exactly the same rate as the station around them. With nothing pushing up on them, they float. You experience a tiny version of this every time you jump. For that brief moment in the air, you're in free fall. You don't feel your weight because nothing is pressing against your feet. The moment is too short to notice, but if you could stretch it out, removing the ground entirely, you'd feel exactly what astronauts feel in orbit. Imagine standing in an elevator when the cable suddenly snaps. A terrifying thought, but focus on the physics. As the elevator falls, you'd float inside it. You wouldn't feel your weight. Now imagine that same elevator drifting far from any planet or star, deep in space. You'd float there too. Einstein realized something remarkable. From inside the elevator, those two situations are indistinguishable. Free fall in a gravitational field feels exactly the same as floating in empty space with no gravity at all. This idea is known as the equivalence principle, one of the cornerstones of general relativity. The opposite is also true. When you stand on Earth, you feel the ground pushing up on your feet. That sensation is your weight. The floor is preventing you from following your natural geodesic through curved space-time. Now imagine a rocket drifting in deep space, far from any stars. If that rocket accelerates upward at 9.8 meters per second squared, the same acceleration caused by Earth's gravity, you would feel the floor pushing against your feet in exactly the same way. From inside the rocket, there's no experiment you could perform to tell whether you're standing on Earth or accelerating through empty space. The experiences are physically equivalent, and this principle leads to some truly strange consequences. One of them is gravitational time dilation. Time itself flows at different rates depending on how strongly space-time is curved. The deeper you are in a gravitational field, the slower time passes. On the surface of a massive planet, where space-time is more distorted, time ticks more slowly than it does for someone higher up, where the curvature is weaker. This isn't a psychological effect. Time doesn't feel slower. It actually is. Time doesn't tick at the same rate everywhere. If you took two perfectly synchronized clocks, placed one on Earth's surface and another in orbit, then brought them back together, they wouldn't agree anymore. The clock that stayed deeper in Earth's gravity would show that less time had passed. This isn't theory. It's been measured directly, again and again. One of the earliest real-world demonstrations happened in 1971. Scientists placed ultra-precise atomic clocks on commercial airplanes and flew them around the planet. When the planes landed, those clocks were slightly ahead of identical clocks left on the ground, by exactly the amount Einstein's equations predicted. The difference was tiny, measured in billionths of a second, but it was unmistakably real. This effect isn't just a curiosity. It's essential to modern technology. GPS satellites orbit high above Earth, where space-time is less curved. Their atomic clocks run slightly faster than clocks on the surface. If this difference weren't corrected, GPS positioning would drift by kilometers within a matter of hours. Every time your phone gives you directions, it's quietly relying on general relativity to work. Einstein's theory predicts more than just warp time. It predicts that light itself follows curved paths. Light doesn't travel in straight lines through the universe. It follows geodesics through space-time. When light passes near a massive object, its path bends. A sufficiently massive object can act like a cosmic lens, distorting and magnifying whatever lies behind it. This effect was first confirmed in 1919 during a total solar eclipse. Astronomers photographed stars near the sun's edge while the sun's glare were blocked. Those stars appeared slightly shifted from their known positions. The sun's gravity was bending their light, and the amount of bending matched Einstein's predictions perfectly. That single observation transformed Einstein into a global celebrity. Today, gravitational lensing is a powerful astronomical tool. When light from a distant galaxy passes near a massive galaxy cluster on its way to us, the light can split into multiple paths. We see duplicated images, glowing arcs, or complete rings of light. By studying these distortions, astronomers can map the mass of the lensing object, including dark matter, which doesn't emit light but still curves space-time. The most extreme space-time distortions occur around black holes. A black hole is a region where space-time is curved so severely that no path leads back out, not even for light. The boundary marking this point of no return is called the event horizon. Cross it, and every possible future path leads inward. Not because something is pulling you, but because space-time itself leaves no alternative. Black holes form when massive stars reach the end of their lives. Throughout a star's existence, gravity tries to compress it while nuclear fusion pushes outward. As long as fusion continues, the star remains stable. But when a sufficiently massive star exhausts its fuel, the outward pressure vanishes. Gravity takes over. If the star is large enough, roughly more than 20 times the mass of our Sun, the collapse never stops. The star's mass compresses into an unimaginably dense region known as a singularity, surrounded by the event horizon. The size of that horizon depends on mass. A black hole with the Sun's mass would have an event horizon about 3 kilometers in radius. 10 times the mass means 10 times the radius. Supermassive black holes, found at the centers of galaxies, can have event horizons larger than entire planetary orbits. From the perspective of someone falling in, crossing the event horizon takes a finite amount of time, seconds, minutes, or hours, depending on the black hole. But to an observer watching from far away, the fallen never quite reaches the horizon. Time dilation grows more extreme. The falling person appears to slow down, their light redshifting, fading from view. Both perspectives are correct. Inside the horizon, space-time is so warped that the future points toward the singularity. Hitting it is as unavoidable as moving forward in time. The singularity isn't a location you can dodge. It's a moment that lies ahead. At that point, our theories fail. General relativity predicts infinite curvature and infinite density, signals that the math has reached its limits. Physicists suspect quantum effects become important long before true infinities appear, but a complete theory of quantum gravity doesn't yet exist. We don't know what really happens at the core of a black hole. Some believe space-time itself dissolves at extremely small scales, replaced by something more fundamental. The singularity may not be a physical point at all, but a breakdown in our description of reality. There's also a principle called cosmic censorship, proposed by Roger Penrose. It suggests that singularities are always hidden behind event horizons, safely sealed away from the rest of the universe. If naked singularities existed, regions where physics completely breaks down would be visible. Predictability itself would fail. So far, nature seems to enforce this rule, though researchers continue searching for exceptions. Despite popular myths, black holes aren't cosmic vacuum cleaners. They don't suck in everything nearby. A black hole pulls on objects gravitationally just like any other mass. If the sun were magically replaced by a black hole of the same mass, Earth's orbit wouldn't change. We'd freeze, but we wouldn't spiral inward. The real danger comes from getting extremely close. Near a black hole, tidal forces become enormous. Gravity pulls hard on the part of you closer to the black hole than on the part farther away. As you fall feet first, the difference in pull stretches your body. Closer still, the stretching becomes fatal. Physicists call this process spaghettification, and yes, that's the real term. For small black holes, this would happen before you even cross the event horizon. For supermassive black holes, the horizon is so large that tidal forces that can be gentle. You could cross without immediate harm, only to be destroyed deeper inside. Black holes aren't completely black. In 1974, Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation. Particle-antiparticle pairs constantly appear in empty space. Near horizon, one particle can fall in while the other escapes. To an outside observer, the black hole appears to glow faintly. This Hawking radiation carries energy away, causing the black hole to slowly lose mass and eventually evaporate. For stellar mass black holes, this process takes an absurdly long time, around 10 years, far longer than the current age of the universe. Only hypothetical tiny black holes would evaporate quickly, possibly exploding in bursts of energy. Another dramatic confirmation of general relativity comes from gravitational waves. Accelerating masses create ripples in space-time that travel outward at the speed of light. Einstein predicted them in 1916, but believed they'd never be detected. A century later, he was proven wrong. In 2015, the LIGO observatories detected space-time stretching and squeezing by less than a fraction of a proton's width. The signal came from two black holes merging 1.3 billion light-years away. In a split second, several solar masses were converted directly into gravitational wave energy. Since then, Dozens of such events have been observed, including neutron-star collisions. These detections opened a new era of multi-messenger astronomy, allowing us to study the universe using both light and space-time itself. Gravitational waves let us probe matter at densities impossible to recreate on Earth, test alternative theories of gravity, and even measure the universe's expansion in new ways. And gravity still holds deeper mysteries. Galaxies rotate too fast to be explained by visible matter alone. Something unseen adds extra gravity. We call it dark matter. It doesn't emit light, but it bends space-time. About 85% of all matter in the universe is dark. Then there's dark energy. In 1998, astronomers discovered that the universe's expansion is accelerating. Something is pushing space itself apart. Dark energy appears to be a property of space, growing stronger as the universe expands. It makes up about 68% of the universe's total energy. That means 95% of the universe is something we don't yet understand. The future consequences are profound. As expansion accelerates, distant galaxies will disappear beyond our cosmic horizon. Far future civilizations may see only their local galaxy, unaware the wider universe ever existed. We're lucky to live at a time when the cosmos is still visible. General relativity doesn't just explain gravity, it describes the evolution of the entire universe. In the 1920s, Einstein's equations revealed that the universe cannot be static. Observations soon confirmed it. Galaxies are receding. Space itself is expanding. Reverse that expansion, and everything converges toward an extremely hot, dense beginning. The Big Bang. Not an explosion in space, but the expansion of space. The evidence is everywhere. Receding galaxies, the cosmic microwave background, and the precise abundance of light elements. The universe began about 13.8 billion years ago. And before that, there is no before. Time itself began with the universe. Asking what came before the Big Bang is like asking what lies north of the North Pole. The question doesn't apply, because time is part of space-time, and space-time is a stage on which everything exists. When space-time came into existence, time itself began with it. There was no earlier moment, no ticking clock before the universe. Asking what happened before the beginning is meaningless, because before requires time, and time did not yet exist. What we can say with confidence starts slightly later. The very first instance after the Big Bang remains speculative. At those extreme temperatures and densities, our current theories break down. To describe that era, we would need a full theory of quantum gravity, a framework that unifies general relativity with quantum mechanics. We don't have one yet. Physicists are actively developing candidates like string theory and loop quantum gravity, but none are complete or experimentally confirmed. Because of this, we can't say exactly what happened in the first tiny fraction of a second. However, from roughly 1 second onward, our theories work extraordinarily well and match observations with remarkable precision. Another question people often ask is whether the universe is infinite. The honest answer is, we don't know. The observable universe is finite. It includes everything from which light has had time to reach us since the Big Bang, a region about 93 billion light-years across. Beyond that boundary lies space we cannot yet observe. But that doesn't mean space ends there. It may extend far beyond what we can see, possibly infinitely. Measurements show that the universe is very close to spatially flat on the larger scales. This is consistent with an infinite universe, but it could also mean the universe is finite yet unbounded, curved back on itself like the surface of a sphere. Finite, but without an edge. At present, we simply don't have enough information to decide. General relativity predicts many other subtle effects, one of which is frame dragging. When a massive object rotates, it doesn't just spin, it drags space-time around with it. For Earth, this effect is incredibly small, but it has been measured. In 2004, NASA launched Gravity Probe B, a satellite carrying ultra-precise gyroscopes so smooth that, scaled to Earth size, their surface bumps will be only a few meters high. Over more than a year in orbit, those gyroscopes detected tiny changes in orientation caused by Earth's rotation twisting space-time itself, exactly as Einstein predicted. Near rotating black holes, frame dragging becomes extreme. A black hole is defined by just 3 properties: mass, electric charge, and spin. Charge is usually negligible, but spin is unavoidable. Stars rotate. and when a rotating star collapses, the resulting black hole spins rapidly. A spinning black hole drags space-time into a violent whirlpool, creating a region outside the event horizon called the ergosphere. Inside the ergosphere, space-time itself is moving so fast that nothing can remain stationary. In principle, energy can be extracted from this motion through the Penrose process. An object enters the ergosphere and splits in two. One piece falls into the black hole, carrying negative energy relative to infinity. The other escapes with more energy than the original object had. The black hole slows down, and usable energy is extracted. It sounds like science fiction, but it follows directly from Einstein's equations. General relativity even allows stranger possibilities, such as closed time-like curves, paths through space-time that loop back to earlier times. Certain mathematical solutions permit this, raising all the familiar paradoxes of time travel. Most physicists suspect such paths can't exist in reality. Quantum effects may destroy them, or the conditions needed to create them may be physically impossible. For now, the question remains open. Despite these mysteries, general relativity has passed every experimental test for over a century. And yet, we know it isn't the final theory. It conflicts with quantum mechanics. Each theory works perfectly in its own domain: quantum mechanics for the microscopic world, general relativity for the cosmic scale. But when both are needed at once, such as inside black holes or at the Big Bang, they disagree. A complete theory of quantum gravity remains one of the greatest unsolved problems in physics. Still, general relativity stands as one of the most successful theories ever created. It predicted black holes, gravitational waves, the expansion of the universe, and the Big Bang long before they were observed. And it all comes down to a single, radical idea. Gravity is not a force. It is the curvature of space-time. Right now, you feel weight. If you're sitting, the chair pushes up on you. If you're standing, the floor presses against your feet. In Newton's picture, this is gravity pulling you downward. But general relativity tells a different story. Your body naturally wants to follow a geodesic, a straight path through curved space-time, one that leads toward Earth's center. The chair or floor resists that motion using electromagnetic forces. What you interpret as weight is not gravity acting on you, but matter preventing you from falling. If the floor vanished, you'd feel weightless, not because gravity stopped, but because nothing would resist your natural motion. You'd be in freefall. Astronauts in orbit feel weightless for exactly this reason. Freefall is a natural state of motion. Weight is the exception. This flips our intuition upside down. We think standing still is normal and falling needs an explanation. General relativity says the opposite. Falling requires no force. Standing still does. This viewpoint explains why all objects fall at the same rate in a vacuum. A feather and a hammer hit the ground together on the moon, because both are following the same space-time paths. There is no force proportional to mass pulling them down, only geometry guiding their motion. In Newton's theory, this equality is a coincidence. In Einstein's theory, it is inevitable. Objects don't fall because they are pulled. They fall because space-time tells them how to move. Space-time curvature doesn't depend on how massive an object is. Geometry treats everything the same. Because all objects follow identical geodesics, they fall at the same rate, not as a coincidence, but as a direct consequence of space-time itself. So why don't you feel gravity while falling? During freefall, every part of your body follows nearly the same path through curved space-time. There's no internal stretching or squeezing, no competing forces acting between your head and your feet. With nothing pushing against you, gravity becomes locally invisible. This is the equivalence principle in action. From your own frame of reference, freely falling in a gravitational field is indistinguishable from floating motionless in deep space. However, this illusion only holds over small regions. Over larger distances or longer durations, differences in space-time curvature begin to matter. These differences produce tidal forces. Your feet may follow a geodesic that curves slightly differently than the one your head follows. Over enough distance, that tiny difference becomes measurable. Near Earth, tidal forces are extremely weak. The International Space Station orbits only about 400 kilometers above the surface, tiny compared to Earth's radius of over 6,000 kilometers. Space-time curvature barely changes across the station's length. Near a black hole, the story is very different. There, Space-time curvature changes dramatically over short distances. Tidal forces grow immense, stretching and compressing objects with catastrophic intensity. General relativity has been tested repeatedly, starting with one of its earliest and most famous predictions, the bending of light by gravity. In Newtonian physics, light shouldn't be affected by gravity because it has no mass. Einstein's theory made a bold claim: light follows geodesics, and space-time curvature should bend its path. In 1919, during a total solar eclipse, expeditions led by Arthur Eddington photographed stars near the sun's edge from Brazil and from the island of Principe off West Africa. The goal was to compare the apparent positions of those stars during the eclipse with their known positions when the sun was elsewhere. Einstein predicted a tiny but measurable deflection. The observations revealed a shift of about 1.75 arcseconds, less than 1/12,000th of a degree, but exactly what general relativity predicted. The result stunned the world. Headlines declared that the laws of the universe had changed overnight. Einstein became an international celebrity. Today, gravitational lensing is observed routinely. Massive galaxy clusters bend light from distant galaxies, producing arcs, rings, and multiple images. Astronomers now use this effect to map invisible matter, revealing the presence and distribution of dark matter across the cosmos. Another classic test involves Mercury's orbit. For decades, astronomers knew that Mercury's perihelion, the point of closest approach to the Sun, shifted slightly with each orbit. Newtonian gravity couldn't fully explain the discrepancy. When Einstein completed general relativity in 1915, one of his first calculations was Mercury's orbit. The theory predicted an extra precession of exactly 43 arcseconds per century. It matched observations perfectly. Einstein later described this moment as one of the happiest of his life. Gravitational redshift provides yet another confirmation. As light climbs out of a gravitational field, it loses energy. Lower energy means lower frequency and longer wavelength, shifting light toward the red end of the spectrum. This effect was first measured directly in 1960 using the Morse-by effect, allowing incredibly precise frequency comparisons. Gamma rays emitted at the top of a tower were detected at the bottom, arriving slightly redshifted, exactly as predicted. Light from the sun shows a small but measurable redshift. From white dwarf stars, the effect is stronger. From neutron stars, it becomes dramatic. Near a black hole's event horizon, the redshift grows extreme. Light barely escaping loses so much energy that its frequency drops towards zero. Gravitational redshift also appears on the larger scales. As the universe expands, space-time itself stretches light traveling through it. By measuring how much a galaxy's light has redshifted, astronomers determine its distance and the age of the universe when that light was emitted. Time itself is affected by gravity. In 2010, researchers at the National Institute of Standards and Technology demonstrated gravitational time dilation over a height difference of just 33 centimeters. Two atomic clocks were placed 1 foot apart vertically. The higher clock ticked slightly faster because it experienced a weaker gravitational field. The difference was only tens of trillionths of a second per day, but it was measurable. Binary pulsars provide another extraordinary test. A pulsar is a rapidly spinning neutron star that emits beams of radio waves. When these beams sweep past Earth, they appear as incredibly regular pulses. Some pulsars orbit another dense object in binary systems. The Hulse-Taylor pulsar consists of 2 neutron stars orbiting each other every 7.75 hours. General relativity predicts such systems should lose energy by emitting gravitational waves, causing the orbit to shrink. Decades of observation showed the orbital period decreasing at precisely predicted rate. This was the first indirect evidence of gravitational waves, long before they were directly detected. That direct detection came in 2015, when LIGO observed gravitational waves from merging black holes. The detected signal matched theoretical predictions in astonishing detail. From the waveform alone, scientists could infer the masses, spins, and distance of the black holes involved. Even in the strongest gravitational fields, Einstein's theory held firm. In 2019, the Event Horizon Telescope captured the first image of a black hole shadow in the galaxy M87, about 55 million light-years away. The size and shape of the shadow matched predictions from general relativity with remarkable accuracy. If gravity behaved differently, the image would look different. It didn't. The Event Horizon Telescope later turned its attention closer to home. It imaged a supermassive black hole at the center of our own galaxy, Sagittarius A star. Once again, the result aligned precisely with what general relativity predicted. These observations push Einstein's theory into some of the harshest environments in the universe, regions near supermassive black holes where space-time is twisted to extremes. And even there, the theory continues to hold. So if general relativity works this well, why do physicists think it might still be incomplete? The answer lies in quantum mechanics. Quantum mechanics governs the microscopic realm, the behavior of electrons, photons, quarks, and other fundamental particles. Unlike general relativity, quantum mechanics is inherently probabilistic. It doesn't describe certainty. It describes likelihoods. Particles don't have definite positions or velocities until they are measured. Before measurement, they exist in a superposition, a blend of many possible states at once. Measurement collapses at superposition into a single outcome. This idea is completely foreign to general relativity. General relativity is deterministic. If you know the geometry of space-time and the positions and velocities of objects at a given moment, the past and future are fully determined. No probabilities, no uncertainty, no overlapping realities. Most of the time, this mismatch isn't a problem. Quantum mechanics handles the very small. General relativity handles the very large. They rarely overlap, but in certain extreme situations, both must apply simultaneously. Inside a black hole, space-time curvature becomes infinite at the singularity. But the scales involved are so small and the density so extreme that quantum effects cannot be ignored. General relativity alone breaks down. The same is true at the beginning of the universe. In the first instant after the Big Bang, the entire cosmos was compressed into a region smaller than an atom. Quantum behavior mattered. Space-time curvature mattered. And our existing theories can't describe both together. We need a theory of quantum gravity. One attempt is string theory. In string theory, particles aren't point-like objects. They are tiny vibrating strings. Different vibration patterns correspond to different particles, electrons, photons, quarks, all manifestations of the same underlying entity. Gravity emerges naturally in this framework. One vibration mode behaves like the graviton, the hypothetical quantum carrier of gravity. String theory also predicts extra dimensions beyond the 3 of space and 1 of time we experience. Most versions require 10 or 11 total dimensions. The additional dimensions are thought to be compactified, curled up so small they are undetectable. Elegant mathematics, bold ideas, but so far, no experimental confirmation. Another approach is loop quantum gravity. Instead of quantizing particles, it attempts to quantize space-time itself. In this picture, space-time isn't smooth and continuous. It's made of tiny, discrete loops, indivisible units of area and volume. This granular structure could eliminate the infinities that plague classical theories. But like string theory, loop quantum gravity has yet to produce testable predictions we can verify. There are other ideas too, theories with higher dimensions, theories where gravity emerges from deeper physical principles. Even proposals suggesting space-time itself may not be fundamental at all. The truth is, we don't know which, if any, is correct. Quantum gravity remains one of the greatest unsolved problems in physics. Until it's solved, parts of reality will remain beyond our understanding. The true nature of the Big Bang, what happens inside black holes, and what ultimately becomes of information that falls into them. So what does all of this mean for you? In everyday life, almost nothing changes. The effects of general relativity are usually too small to notice. Your phone relies on relativistic corrections for GPS to work properly, but you never think about it. The time dilation between standing up and sitting down amounts to only about 10 trillionths of a second per day. Completely imperceptible. And yet, it matters. It matters because general relativity changes how you understand reality. You live in a universe where space and time are not separate. They are fused into space-time. That space-time is not rigid. It bends and curves in response to mass and energy. You are not held to Earth by an invisible pulling force. You are following the natural contours of curved space-time. Every object, from a grain of sand to a galaxy cluster, shapes space-time around it. These curvatures interact, producing complex cosmic dance we observe. Planets orbiting stars, stars circling galactic centers, galaxies clustering across the universe. All of it is matter following geodesics through a constantly evolving four-dimensional geometry. When you look up at the night sky, you are not just seeing distant objects, you are seeing the past. Sunlight reaching your eyes left the sun 8 minutes ago. Light from the nearest star began its journey more than 4 years ago. Light from distant galaxies has traveled for billions of years. The universe records its history in light, and that light has traversed curved space-time to reach you. You are part of that history. The atoms in your body were forged in stars long before Earth existed. Those stars exploded as supernovae, scattering their material across space. Over vast spans of time, that matter gathered, collapsed, and formed our solar system. After billions of years of cosmic and biological evolution, those atoms arranged themselves into you. This isn't poetry. It's chemistry and astrophysics. The carbon in your cells, the iron in your blood, the calcium in your bones, all were created in stellar furnaces and explosive deaths of stars. General relativity reveals that space-time is not a passive stage where events happen. It is an active participant. Matter and energy curve space-time. That curvature directs motion. Motion reshapes space-time in return. A continuous feedback loop. From falling apples to black hole mergers to the expansion of the universe itself. There's a deeper implication here. In Newton's view, space and time were absolute, fixed backgrounds that existed independently of matter. Einstein showed this picture is wrong. Space-time is relational. It is defined by the objects and events within it. Remove all matter and energy, and it's not clear space-time would exist at all in any meaningful sense. The universe isn't a container holding things. The universe is the things, and the relationships between them. Space-time is those relationships, and that changes everything. The universe is complete in itself. There is no outside. Asking what lies beyond the universe doesn't really make sense, because the idea of outside assumes space, and space is part of the universe. In the same way, asking what happened before the Big Bang may be a misplaced question. If time itself began with the Big Bang, then there was no earlier moment for something to happen in. These questions feel natural to ask. Our minds are wired to think in terms of before, after, inside, and outside. But at the most fundamental level of reality, those concepts may simply stop applying. Some people find this deeply unsettling. The universe offers no external explanation. It doesn't sit inside something bigger. It isn't caused by something else in a meaningful temporal sense. The universe is the explanation. Others find this idea liberating. Reality is intelligible on its own terms. We don't need to appeal to anything beyond it to understand how it works. The laws of physics, the structure of space-time, and the constants of nature form the foundation. Everything else emerges from there. So where is gravitational physics headed? One major direction is pushing general relativity into even more extreme regimes. The Event Horizon Telescope continues to observe black holes, searching for even the smallest deviations from Einstein's predictions, tiny discrepancies that could point toward new physics. Future observations aim to track matter as it spirals into black holes in real time, watching how warped space-time shapes the paths of glowing gas just before it vanishes. Of particular interest is the photon ring, a thin, brilliant band of light formed by photons that orbit the black hole multiple times before escaping. Its exact shape and brightness carry detailed information about the black hole's spin and geometry. Measuring it precisely will test general relativity more rigorously than ever before. Gravitational wave astronomy is also advancing rapidly. LIGO is being upgraded. New ground-based detectors are coming online in Japan and India. And in the 2030s, LISA, the Space-Based Gravitational Wave Observatory, is scheduled to launch. Unlike ground detectors, LISA will be sensitive to low-frequency gravitational waves. This will allow it to observe mergers of supermassive black holes when entire galaxies collide, events too slow and massive for Earth-based instruments to detect. Each observation will probe gravity under conditions of unimaginable violence, adding further confirmation, or potential challenges, to Einstein's equations. Gravitational waves are more than just confirmations of theory. They are a new scientific tool. When neutron stars collide, the gravitational wave signal encodes information about the structure of matter at densities far beyond anything we can reproduce on Earth. Inside neutron stars, atomic nuclei are crushed together into exotic states of matter that exist nowhere else. Different models of how matter behaves at these densities predict slightly different gravitational wave patterns. By analyzing those patterns, we're effectively performing experiments on matter compressed to extremes nature alone can achieve. Another frontier lies at the intersection of gravity and quantum mechanics. Quantum gravity experiments are extraordinarily difficult because quantum gravitational effects are expected to become significant only at the Planck scale, around 10 cubed meters, far smaller than any structure we can directly probe. Building machines capable of reaching those energies is impossible with current technology, but there may be indirect clues. If space-time is fundamentally discrete rather than continuous, that structure could subtly influence how light travels across vast cosmic distances. Photons of different energies might move at slightly different speeds through quantized space-time, arriving at Earth with tiny delays after traveling billions of years. So far, no such effects have been observed. That absence is itself important. It has already ruled out entire classes of quantum gravity theories that predicted detectable deviations. There are also experiments exploring whether gravity affects quantum superpositions. Quantum objects can exist in multiple states at once, until measured. But what happens when those objects become massive enough for their gravitational influence to matter? Can space-time itself become entangled with quantum states? Is it possible to have a superposition of different space-time geometries? Experiments placing increasingly large objects, molecules, nanoparticles, even microscopic mirrors, into quantum superpositions may reveal where quantum behavior gives way to classical space-time, offering hints toward the correct theory of quantum gravity. Meanwhile, astronomers are using gravity as a precision tool. Gravitational lensing allows us to observe galaxies that would otherwise be invisible, magnified by the curvature of space-time created by massive foreground objects. By mapping how light bends, we can trace the distribution of dark matter in galaxy clusters. Lensing can even reveal exoplanets. When a planet's gravity briefly focuses light from a background star, it creates a characteristic brightening, a fleeting signal that betrays a planet's presence. In more dramatic cases, lensing produces Einstein rings or Einstein crosses, where a single distant quasar appears as multiple images around a foreground galaxy. Light takes several paths through curved spacetime, each arriving at Earth at a slightly different time. By measuring those time delays, astronomers can calculate the universe's expansion rate without relying on traditional distance ladders. This method provides an independent check on one of the biggest open questions in cosmology: how fast the universe is really expanding. There's also the possibility of detecting primordial gravitational waves, ripples in space-time generated in the universe's earliest moments. These waves would carry information from an era far earlier than any light we can observe. Detecting them would open a direct window into the universe when it was less than a fraction of a second old. Scientists search for these ancient waves in the cosmic microwave background, the afterglow of the Big Bang. Gravitational waves passing through the early universe would have imprinted a distinctive swirling pattern in the polarization of this radiation, known as B modes. Finding them would be a smoking gun for cosmic inflation, a brief period of explosive expansion shortly after the Big Bang. It would reveal the energy scale of inflation and probe physics at energies trillions of times higher than those reached in particle accelerators. Beyond theory, understanding gravity has real technological consequences. GPS works only because relativistic effects are accounted for. Gravitational wave detectors push the development of ultra-stable lasers, extreme vibration isolation, and unprecedented measurement precision. These technologies now benefit fields ranging from telecommunications to atomic clocks and materials science. Looking further ahead, some physicists speculate about manipulating space-time itself for propulsion. Instead of moving through space, a spacecraft might alter space-time around it, contracting space in front and expanding it behind. The Alcubierre warp drive is the most famous example, mathematically allowed by general relativity, but requiring exotic forms of energy that may not exist. Still, the fact that such solutions are permitted at all highlights how radically different Einstein's theory is from Newtonian gravity. More realistically, gravity research may help solve long-term spaceflight challenges. Rotating habitats already use centrifugal acceleration to simulate gravity, an application of the equivalence principle. Future designs could create variable gravity environments to support human health on long-duration missions. General relativity has transformed our understanding of a universe. It isn't just an improved version of Newton's ideas. It's a fundamentally new way of thinking about space, time, motion, and causality. And every experiment so far has confirmed it. One person, working largely through thought experiments, reshaped our picture of the cosmos, from subatomic scales to the largest structures in existence. That alone is extraordinary. But the story isn't finished. We know general relativity is incomplete. We still don't understand dark matter or dark energy, which together make up most of the universe. We don't know whether the cosmos is finite or infinite, whether it will expand forever or collapse, or whether other universes exist beyond our own. These questions remain open, and that's what makes the universe exciting. There is still so much left to uncover. One day, scientists of the future will look back on our era the way we look back on Newton's time. They'll admire how much we understood, but they'll also clearly see what we missed, the unanswered questions, the limits of our tools, the ideas we couldn't yet imagine. That's how science works. It isn't a finished book. It's an ongoing process of refinement. Each generation inherits a framework, tests it, improves it, and passes something stronger to the next. We're not standing at the end of knowledge. We're standing in the middle of a long journey. So what should you take away from all of this? First, gravity is not a force in the ordinary sense. It isn't an invisible pull reaching across space. Gravity is geometry. Mass and energy bend space-time, and objects move along the natural paths, geodesics, within that curved structure. When you feel weight, you're not feeling gravity itself. You're feeling electromagnetic forces pushing back on you, preventing you from following your natural free-fall path. When you fall freely, that resistance disappears, and so does the sensation of weight. Second, space and time are not separate things. They are woven together into space-time. And space-time isn't rigid. It responds to mass and energy, curving and evolving. That curvature shapes motion, and moving matter reshapes curvature in return. This feedback loop gives rise to everything from falling apples to orbiting planets, from galaxy formation to the expansion of the universe itself. Third, general relativity is one of the most thoroughly tested theories in all of science. From Mercury's orbit to gravitational waves, from time dilation measured by atomic clocks to images of black hole shadows, every experiment so far has confirmed Einstein's predictions. Your phone's GPS works only because relativistic effects are corrected. Gravitational lensing lets us map dark matter. Gravitational waves have opened an entirely new way to observe the universe. Few theories in history have succeeded so completely. Fourth, despite that success, general relativity is not the final word. It does not include quantum mechanics. To understand reality at its deepest level, inside black holes, at the birth of the universe, at the Planck scale where space-time itself may become granular, we need a theory of quantum gravity. That theory remains elusive. String theory, loop quantum gravity, and other approaches are still competing to unify our understanding. This is one of the greatest challenges in modern physics. Fifth, these ideas are not just abstract philosophy. They have real applications. Gravitational lensing helps astronomers see farther than ever before. Gravitational waves reveal events invisible to traditional telescopes. Precision technologies developed for relativistic experiments, atomic clocks, laser stabilization, vibration isolation, now benefit navigation, communications, and fundamental research. Understanding gravity helps us understand stars, planets, galaxies, and the structure of the cosmos itself. And finally, there's something deeply profound about realizing the kind of universe you live in. Space-time isn't just a mathematical abstraction. It's the fabric of reality. Every moment of your life, you're moving through it, following geodesics, experiencing time differently from other observers, interacting with curvature created by Earth, the Sun, the galaxy, and the mass energy of the entire universe. You are part of a cosmic process that began nearly 14 billion years ago and will continue for trillions more. When you drop a ball, you're not watching a force pull it downward. You're watching it follow the natural geometry of space-time. When you look at the moon, you're seeing an object in continuous free fall, endlessly circling Earth because that is a path space-time provides. When you feel your weight, it's because the ground is pushing you upward, preventing you from falling freely along your natural trajectory toward Earth's center. Nothing here is intuitive, but all of it is real. Light from distant galaxies has traveled for billions of years through expanding space-time to reach your eyes. Gravitational waves from black holes colliding far away ripple through space-time itself. Black holes sit where curvature becomes so extreme that even light cannot escape. All of this follows from a single idea: gravity is geometry. It has been more than a century since Einstein published general relativity. In that time, the theory has survived every experimental test. It has predicted phenomena that once sounded absurd and then turned out to be true. It has given us a universe far stranger and more beautiful than anyone expected. We live in a universe where time flows at different rates, where space-time bends and ripples, where the history of the cosmos is written in ancient light crossing unimaginable distances. If you've stayed with this journey to the end, thank you. Understanding these ideas won't change how heavy you feel tomorrow. Objects will still fall. The ground will still feel solid beneath your feet. But you'll know what's really happening beneath the surface, and that deeper understanding has value on its own. As Einstein once said, the most astonishing thing about the universe is that it can be understood. We are small beings on a small world, yet we measure the curvature of space-time, detected ripples from black holes merging 1 billion light-years away, and trace the universe back to its earliest moments. That should give you hope. We are not powerless in the face of cosmic mystery. We can learn. We have learned, and we will continue to learn more. Gravity is not a force pulling you down. It is the shape of space-time itself, and you are moving through it every second of your life. In our solar system, gravity is ruled by one overwhelming presence: our star. The Sun contains about 99.86% of the total mass of the entire system. That enormous mass shapes everything around it. Planets don't wander randomly. They move along precise, predictable paths. Those paths are ellipses, a fact first described by Johannes Kepler in the early 1600s. Kepler discovered how planets move. Isaac Newton later explained why they move that way, through his law of gravitation. And Albert Einstein went even deeper, revealing the underlying mechanism. The Sun bends space-time, and planets follow the natural paths, geodesics, through that curved geometry. The planets themselves also curve space-time, but on a much smaller scale. Earth's gravity holds the moon in its orbit. Jupiter, far more massive, dominates an enormous region of space. With at least 95 known moons, Jupiter's gravitational influence extends deep into the asteroid belt, shaping its structure in dramatic ways. Within the asteroid belt are regions called Cokewood gaps, zones where very few asteroids are found. These gaps occur at orbital distances where an asteroid period would be a simple fraction of Jupiter's orbital period, like 1/3 or 1/2. In those locations, asteroids receive repeated gravitational nudges from Jupiter at the same point in their orbit. Over time, these rhythmic tugs alter their paths, ejecting them from those regions entirely. Gravity, acting through orbital resonance, clears the gaps. A similar process sculpts Saturn's rings. The rings consist of countless particles, ice and rock ranging from microscopic dust to massive boulders, all orbiting in a thin disk. Yet the rings are not uniform. They contain sharp divisions and gaps. The most famous, the Cassini division, exists because particles that resonate with one of Saturn's moons. Repeated gravitational disturbances sweep the region clean. Other small moons act as shepherds, corralling ring particles into narrow bands. Its gravity-imposing structure on chaos. Far beyond the planets lies the Oort cloud, a vast spherical shell of trillions of icy bodies extending nearly a light-year from the Sun. Occasionally, a passing star or the tidal pool of the galaxy disturbs one of these objects. The result is a comet sent plunging toward the inner solar system. As it approaches the Sun, heat releases gas and dust, forming glowing tails. Sometimes, gravity leads to collision. In 1994, Comet Shoemaker, Levi 9 wandered too close to Jupiter. Tidal forces tore it apart into fragments, which then slammed into Jupiter's atmosphere over several days. Each impact released energy equivalent to millions of nuclear weapons. Dark scars lingered in Jupiter's clouds for months. Gravity choreographed every step, from disruption to destruction. On even larger scales, gravity both creates and destroys stars. Stars are born inside enormous molecular clouds, hundreds of light years wide. If a region becomes slightly denser than its surroundings, gravity pulls in more material, increasing its density and accelerating collapse. As matter falls inward, gravitational energy turns into heat. The core grows hotter and denser until temperatures reach millions of degrees. Hydrogen fusion ignites. Outward pressure from fusion balances inward gravity. The star enters hydrostatic equilibrium and begins its long, stable life. Our Sun formed about 4.6 billion years ago and is roughly halfway through its 10 billion year main sequence lifespan. Eventually, its hydrogen fuel will run out. Fusion will slow. Gravity will regain the upper hand. The core will contract and heat until helium fusion begins, transforming the Sun into a red giant. In about 5 billion years, it will expand beyond Earth's current orbit. For more massive stars, the process continues through multiple fusion stages: helium into carbon, carbon into neon, oxygen, silicon, and finally iron. Each stage releases less energy and lasts for a shorter time. Iron marks the end. Fusing iron consumes energy instead of producing it. When an iron core forms, fusion stops entirely. Gravity takes over. The core collapses in a fraction of a second. Electrons are crushed into protons, forming neutrons. The collapse rebounds, launching a shock wave that tears the star apart in a supernova. For weeks, the explosion can outshine entire galaxies. Heavy elements are forged and hurled into space. Every element heavier than helium, carbon, oxygen, iron, calcium was created this way. You are made of that debris. Gravity formed the stars, crush their cores, trigger their explosions, and then gather the remnants to form new stars, planets, and eventually Earth. Some stellar remnants become neutron stars, among the most extreme objects known. Roughly 1.4 times the Sun's mass compressed into a sphere only about 20 kilometers across. Their density is so extreme that a teaspoon of neutron star material would weigh billions of tons. Surface gravity is hundreds of billions of times stronger than Earth's. Light escaping the surface is significantly redshifted. Many neutron stars spin hundreds of times per second. Powerful beams of radiation stream from their magnetic poles. As a star rotates, the beams sweep through space. If one crosses Earth, we observe perfectly timed flashes, pulsars. Their precision is so remarkable that when pulsars were first discovered in 1967, scientists briefly considered whether they might be artificial signals. Nature turned out to be even more extraordinary. For the most massive stellar cores, not even neutron pressure can stop collapse. If the core exceeds roughly 3 solar masses, gravity overwhelms all resistance. The object collapses into a black hole. Matter compresses beyond our current understanding into a singularity. An event horizon forms, a boundary beyond which space-time itself funnels everything inward. No signal, not even light, can escape. Black holes come in many sizes. Stellar mass black holes form from supernovae. At the other extreme are supermassive black holes, containing millions or billions of solar masses lurking at the centers of galaxies. How they formed is still debated, but gravity drove every step of their growth. At the heart of our own galaxy lies one such object, Sagittarius A star. It has a mass of about 4 million suns. Astronomers have tracked stars orbiting it with extraordinary precision. One star, known as S2, completes an orbit in just over 16 years and reaches speeds of nearly 2% the speed of light at closest approach, moving through space-time warp almost beyond comprehension. From planets to rings, from stars to black holes, gravity shapes the universe at every scale. By tracking the motion of stars near the galactic center, astronomers confirmed something extraordinary. An invisible object with immense mass was lurking there, one that could only be a black hole. These stars move at tremendous speeds, following tight, highly curved orbits. No cluster of normal objects could remain stable under such conditions. Only a single, compact source of gravity fits the data. That conclusion was dramatically confirmed when the Event Horizon Telescope captured an image of glowing gas swirling around Sagittarius A asteroid, revealing the shadow of the black hole itself. The size and shape of that shadow matched the predictions of general relativity with remarkable precision. Supermassive black holes influence far more than their immediate surroundings. Their gravitational reach extends across entire galaxies. Stars orbit galactic centers for the same reason planets orbit stars, not because they are being pulled in the Newtonian sense, but because they are following geodesics through space-time curved by the central mass. The Milky Way is a barred spiral galaxy roughly 100,000 light-years wide, containing between 200 and 400 billion stars. Every one of them is bound by gravity, orbiting the galactic center. Our sun lies about 26,000 light-years from that center. At this distance, a single galactic orbit takes approximately 225 million years. The last time the sun occupied its current position, dinosaurs were just beginning to appear on Earth. Galaxies themselves are not rigid objects. They are vast gravitational systems, billions of stars, clouds of gas, and dark matter bound together. When galaxies pass near one another, gravity distorts them. Spiral arms stretch and twist. Streams of stars are pulled free. Sometimes, galaxies merge entirely. The Milky Way is currently in the process of absorbing the Sagittarius dwarf galaxy, a smaller companion being torn apart by tidal forces. Its stars now form long, looping streams that wrap around our galaxy, fossil evidence of an ongoing major. At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole with a mass of about 4 million suns. Some stars orbit it in just a few years. One of them, S2, swings so close that it reaches speeds of nearly 2% the speed of light, moving through space-time warp to an extreme degree. These observations leave no doubt. A black hole dominates a galactic center. In roughly 4 billion years, gravity will orchestrate an even grander event. The Andromeda Galaxy, currently approaching us at about 110 kilometers per second, will collide with the Milky Way. The encounter will unfold over hundreds of millions of years. Individual stars are unlikely to collide. The distances between them are vast, but gas clouds will compress, igniting intense bursts of star formation. The night sky would be filled with distorted galactic structures and brilliant newborn stars. Eventually, the two galaxies will merge into a single, massive elliptical galaxy, with a central black hole containing tens of millions of solar masses. Such collisions are common across the universe. Gravity drives galaxy growth through mergers. Small galaxies combine into larger ones, a process ongoing since the first galaxies formed more than 13 billion years ago. Galaxies are not scattered randomly. They gather into groups and clusters. The Milky Way belongs to the local group, a collection of roughly 80 galaxies spanning about 10 million light-years, with a total mass near 2 trillion solar masses, most of it in the form of dark matter. Far beyond lies the Virgo cluster, about 54 million light-years away, containing roughly 1,500 galaxies and a mass exceeding 1 quadrillion solar masses. Our local group is slowly falling toward it under gravity's pull. On the larger scales, the universe resembles a cosmic web. Galaxies trace long filaments stretching across hundreds of millions of light-years, surrounding vast, nearly empty voids. At the intersections of these filaments lie massive galaxy clusters. This structure emerged from tiny density fluctuations in the early universe. Slightly denser regions exerted slightly stronger gravity, pulling in more matter and growing ever denser. Over billions of years, gravity amplified those subtle differences into the immense architecture we observe today. One of gravity's most counterintuitive consequences is gravitational time dilation. Time itself passes at different rates depending on the strength of gravity. The stronger the gravitational field, the more slowly time flows relative to regions of weaker gravity. This is not theory or metaphor. It has been directly measured and must be accounted for in technologies like GPS. Gravity doesn't just shape motion and structure. It shapes time itself. This is not theory. It is a measured fact, confirmed by countless experiments. Take two identical atomic clocks, the most precise timekeepers ever built. Place one on the ground. Carry the other up a mountain. The clock at higher altitude, farther from Earth's center and in a slightly weaker gravitational field, will run faster. When the clocks are reunited, they no longer agree. The difference is tiny, about a millionth of a second per day for a typical mountain, but it is real, measurable, and exactly what general relativity predicts. Time does not flow at a universal rate. The closer you are to mass, the more space-time is curved, and the slower time passes. On Earth, the effect is small. Our planet isn't very massive by cosmic standards, but near extreme objects, time dilation becomes dramatic. Near a neutron star, time passes roughly 30% slower than far away. Near a black hole's event horizon, time dilation becomes infinite. From the perspective of a distant observer, time appears to freeze at the horizon. Yet for someone falling in, nothing special happens at that boundary. They cross the horizon without noticing anything unusual. This difference in perspective leads to one of the deepest puzzles in modern physics. The black hole information paradox. According to general relativity, anything that falls into a black hole is gone forever. Information cannot escape. But according to quantum mechanics, information cannot be destroyed. It may be scrambled, hidden, or transformed, but it must persist. These two principles are fundamentally incompatible. In quantum mechanics, the evolution of a system is reversible in principle. Given complete information at one time, you can calculate the past or future exactly. But if information disappears into a black hole, that reversibility is broken. The universe forgets. That violates unitarity, a cornerstone of quantum theory. Stephen Hawking initially argued that information truly was lost, that black holes were the one place where quantum mechanics failed. This idea shocked physicists and sparked decades of debate. Eventually, Hawking reversed his position, suggesting that information might be encoded in subtle correlations within Hawking radiation, the faint glow emitted as black holes slowly evaporate. How that works remains unclear. One promising idea is the holographic principle, the notion that all the information inside a volume of space can be encoded on its boundary. For a black hole, that boundary is the event horizon itself. Information about everything that falls and may be stored there and gradually releases as the black hole evaporates. Resolving this fully requires a theory of quantum gravity, which we do not yet have. Another profound implication of relativity is that nothing can travel faster than light, not because light is special, but because it defines the structure of space-time itself. Light travels along null geodesics, the boundary between paths objects with mass can follow and paths that would require moving backward in time. The speed of light is the speed of causality, the fastest rate at which information can propagate. Objects with mass must always move slower. As they accelerate closer to light speed, the energy required increases without bound. Reaching light speed would require infinite energy. It is impossible. This has enormous consequences for space travel. Distances between stars are measured in light years. Even at speeds close to light, journeys take years from Earth's perspective. But due to time dilation, travelers experience far less time. If you travel to a star 10 light years away at 99% the speed of light, the trip would take just over 10 years as measured on Earth. But you would experience only about 1.5 years. Upon returning, you might have aged 3 years, while more than 20 pass on Earth. You would have traveled into the future. This is the so-called twin paradox. One twin stays behind. The other travels at high speed and returns younger. There is no paradox. The situations are not symmetric. The traveling twin accelerates and decelerates, breaking the symmetry. The mathematics predicts the outcome exactly, and it had been confirmed experimentally using atomic clocks and high-energy particles. At even higher speeds, the effect becomes extreme. At 99.9% of light speed, a journey across the Milky Way, 100,000 light years, would take 100,000 years from Earth's perspective, but the traveler would experience only about 4,400 years. Still long, but unimaginably shorter than the time passing elsewhere. This is not speculation. In particle accelerators, unstable particles moving near light speed live far longer than their stationary counterparts. Time dilation is real. The universe imposes a cruel trade. Travel far and fast enough, and you can cross enormous distances within a lifetime, but everyone you leave behind will be long gone. Interstellar travelers become temporal exiles, separated not just by space, but by time. The expansion of the universe raises equally profound questions. Will it expand forever? Will gravity eventually reverse it in a big crunch? The answer depends on the universe's total energy density. Measurements show the universe is close to the critical density, but there is a twist. The expansion is not slowing. It is accelerating. This was discovered in 1998 by observing distant supernovae. The result was shocking. Something is pushing space itself apart. We call it dark energy. We do not know what dark energy is. It may be a property of empty space, a cosmological constant, or something more exotic, but we know its effect. Dark energy makes up about 68% of the universe. Dark matter accounts for roughly 27%. Ordinary matter, everything we can see, makes up only 5%. The universe is dominated by the unknown. As expansion accelerates, distant galaxies will eventually slip beyond our cosmic horizon. In trillions of years, only galaxies gravitationally bound to our local group will remain visible. Beyond that, stars will stop forming. Existing stars will burn out. White dwarfs will cool. Black holes will evaporate. The universe will drift toward heat death, dark, cold, and dilute. That future lies unimaginably far ahead. For now, the universe is alive. Stars are forming. Galaxies are colliding. Black holes are growing. And on a small planet, a species capable of curiosity is trying to understand it all. General relativity gives us the tools to do that, from falling apples to black hole mergers to the expansion of space-time itself. It places hard limits on what is possible, but it also reveals astonishing beauty. We may never reach the stars. The speed of light may forever isolate civilization from one another. But even within those limits, we can understand. We can measure space-time curvature, detect gravitational waves from colliding black holes billions of light years away, reconstruct cosmic history back to the first moments after the Big Bang. And that may be the most remarkable thing of all. We are small beings on a small world, and yet we've uncovered the laws that govern the entire cosmos. That alone is astonishing. Gravity links everything, not through an invisible pull, but through the graceful geometry of curved space-time. It shapes worlds and stars, holds galaxies together, and steers the long-term evolution of the universe itself. Understanding gravity through general relativity stands among humanity's greatest intellectual accomplishments. It represents centuries of curiosity and careful thought, from Galileo's observations to Kepler's laws to Newton's insights, and finally to Einstein's revolutionary leap. Each generation tested ideas, refined them, and pushed closer to the truth. Gravity does impose limits. It makes travel between the stars brutally difficult. It sets hard boundaries on speed and energy. But gravity is also the reason anything exists at all. Without it, stars would never ignite. Planets would never assemble. Matter would remain a thin, diffuse fog drifting endlessly through space. No structure, no complexity, no life. Gravity is what gives a universe shape and meaning. Many mysteries remain. Dark matter and dark energy dominate the cosmos, yet we barely understand them. Quantum gravity eludes us. The first moments of the universe and the interiors of black holes remain hidden. Still, general relativity provides a foundation. Whatever comes next will build upon it, not replace it. The central idea that gravity is a curvature of space-time, not a conventional force, will endure. It is a deep truth about how reality works. So keep looking up, keep questioning, keep trying to understand. The universe is vast, strange, and complex, but it is not unknowable. We can understand it. We are understanding it. And simply by asking these questions, you are already part of that journey. You are not being dragged downward by gravity. You are following a natural path through curved space-time. You are riding the geometry of the universe itself. And that is incredible.